question involves determining the appropriate size of the equipment grounding conductor for a 150 amp service when using 1/0 wire. According to electrical codes, specifically referencing the National Electrical Code, the size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. In this case, with the 150 amp service, the applicable table within the NEC dictates the minimum size for the equipment grounding conductor. For a 150 amp service, the minimum size for an equipment grounding conductor, if using copper, is 6 AWG. If using aluminum, the minimum size is 4 AWG. It is crucial to always consult the latest edition of the NEC in the specific tables related to grounding conductor sizing to ensure compliance with all applicable electrical codes and regulations. Now let's delve deeper into the specifics of selecting the correct equipment grounding conductor size for a 150 amp service. The NEC provides tables that correlate the size of the overcurrent protective device, such as a circuit breaker or fuse, with the minimum required size of the equipment grounding conductor. The purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of the overcurrent protective device and clearing the fault quickly. This is essential for safety, as it helps to prevent electrical shock hazards and minimize the risk of fire. When selecting the equipment grounding conductor size, it is important to consider the ampacity of the conductors used for the service. The ampacity refers to the current carrying capacity of a conductor, which is determined by factors such as the conductor material, size, insulation type, and installation conditions. The NEC provides tables that list the ampacities of various conductors under different conditions. The equipment grounding conductor must be sized appropriately to handle the maximum fault current that could potentially flow through it. This is typically determined by the available fault current at the service entrance. The available fault current is the maximum amount of current that the electrical system can deliver during a short circuit condition. It is influenced by factors such as the utility transformer size, impedance of the service conductors, and impedance of the electrical system within the building. To determine the appropriate equipment grounding conductor size, you should first identify the size of the overcurrent protective device protecting the service. In this case, it is a 150 amp circuit breaker or fuse. Next, consult the NEC table that correlates the overcurrent protective device size with the minimum required equipment grounding conductor size. As previously mentioned, for a 150 amp service, the minimum size for an equipment grounding conductor, if using copper, is 6 AWG. If using aluminum, the minimum size is 4 AWG. It is important to note that these are minimum sizes, and in some cases, it may be necessary to use a larger conductor size to meet specific requirements or to provide additional safety margin. For example, if the available fault current is particularly high, a larger equipment grounding conductor may be required to ensure that it can safely handle the fault current. In addition to sizing the equipment grounding conductor correctly, it is also important to ensure that it is properly installed. The equipment grounding conductor must be securely connected to the service equipment enclosure and to any other metal parts that are likely to become energized in the event of a fault. This includes metal conduit, metal enclosures, and metal equipment frames. The connections must be made using approved methods, such as grounding lugs or clamps, and they must be properly tightened to ensure a low impedance connection. It is also important to ensure that the equipment grounding conductor is continuous and unbroken throughout its entire length. This means that it should not be spliced or interrupted in any way. If it is necessary to extend the equipment grounding conductor, the connection must be made using an approved method that maintains the continuity of the conductor. Furthermore, it is important to consider the type of grounding system used in the installation. There are several different types of grounding systems, including grounded systems and rounded systems, and impedance grounded systems. Each type of grounding system has its own specific requirements for equipment grounding conductors. In a grounded system, the neutral conductor is intentionally connected to ground at the service entrance. This provides a low impedance path for fault current to return to the source. The equipment grounding conductor is then connected to the neutral conductor at the service entrance, providing a redundant path for fault current. In an ungrounded system, the neutral conductor is not intentionally connected to ground. In this case, the equipment grounding conductor provides the only path for fault current to return to the source. Because of this, the equipment grounding conductor must be sized appropriately to handle the maximum fault current that could potentially flow through it. In an impedance-grounded system, the neutral conductor is connected to ground through an impedance such as a resistor. This limits the amount of fault current that can flow in the event of a ground fault. The equipment grounding conductor is then connected to the neutral conductor at the service entrance, providing a path for fault current. Regardless of the type of grounding system used, it is essential to follow all applicable electrical codes and regulations when installing equipment grounding conductors. This will help to ensure the safety of the electrical system and minimize the risk of electrical shock hazards and fire. To reiterate, selecting the correct equipment grounding conductor size for a 150 amp service requires careful consideration of several factors, including the size of the overcurrent protective device, the ampacity of the conductors, the available fault current, the type of grounding system, and all applicable electrical codes and regulations. For a 150 amp service, a 6 AWG copper or 4 AWG aluminum conductor is typically the minimum required size for the equipment grounding conductor. However, it is always best to consult the latest edition of the NEC and the specific tables related to grounding conductor sizing to ensure compliance with all applicable requirements. Remember that proper grounding is a critical aspect of electrical safety, and it is essential to take the necessary steps to ensure that the equipment grounding conductor is correctly sized and installed. Always consult with a qualified electrician if you have any questions or concerns about grounding requirements. Grounding and bonding are very important. Let's explore bonding. Bonding ensures electrical continuity and conductivity of metal parts likely to become energized. The purpose of bonding is to create a low impedance path for fault current, facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock. The NEC specifies requirements for bonding various metal components of an electrical system. Bonding jumpers are used to connect metal enclosures, raceways, and equipment together. The size of the bonding jumper is determined by the size of the circuit conductors or the overcurrent protective device. Bonding must extend to all metal parts that could become energized. This includes metal water pipes, gas pipes, and structural steel. Proper bonding is essential for safety and helps to prevent electrical hazards. The main bonding jumper connects the equipment grounding conductor to the grounded conductor at the service equipment. This connection provides a path for fault current to return to the source. The size of the main bonding jumper is determined by the size of the service entrance conductors. Bonding is required for all metal enclosures containing electrical conductors or equipment. This includes panel boards, junction boxes, and motor control centers. Bonding ensures that these enclosures are at the same electrical potential as the equipment grounding system. Bonding is also required for metal raceways, such as conduit and cable trays. This helps to prevent voltage differences between the raceway and the equipment grounding system. Bonding must be continuous and permanent. Connections must be made using approved methods such as bonding lock nuts or grounding bushings. In addition to equipment grounding and bonding, surge protection is another important aspect of electrical safety. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD are installed at the service entrance and at sensitive equipment locations. SPD work by diverting surge current to ground, preventing it from damaging electrical equipment. The NEC provides requirements for the installation and selection of SPD. SPD are rated by their surge current capacity and their voltage protection level. It is important to select an SPD that is appropriate for the specific application. SPD are available in a variety of types, including plug-in SPD, hardwired SPD, and surge protective receptacles. Proper surge protection is essential for protecting sensitive electronic equipment from damage. Another important aspect of electrical safety is ground fault circuit interrupters, or GFCIs. GFCIs are used to protect people from electrical shock hazards. GFCIs work by monitoring the current flowing through a circuit. If the current flowing into the circuit differs from the current flowing out by a small amount, the GFCI will trip, interrupting the circuit and preventing electrical shock. GFCIs are required in locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. The NEC specifies the locations where GFCIs are required. GFCIs are available in a variety of types, including receptacle GFCIs and circuit breaker GFCIs. Regular testing of GFCIs is recommended to ensure that they are functioning properly. Ground fault protection of equipment, or GFP, is another important safety measure. GFP is used to protect electrical equipment from damage caused by ground faults. GFP works by monitoring the current flowing through the equipment grounding conductor. If the current exceeds a certain threshold, the GFP will trip, interrupting the circuit and preventing damage to the equipment. GFP is required for certain types of equipment, such as large motors and generators. The NEC specifies the requirements for GFP. GFP is typically provided by a ground fault relay and a current transformer. Regular testing of GFP is recommended to ensure that it is functioning properly. In summary, selecting the correct equipment grounding conductor size for a 150 amp service is a critical aspect of electrical safety. Following the guidelines provided in the NEC, using appropriate grounding and bonding techniques, and incorporating surge protection and ground fault protection can help to ensure a safe and reliable electrical system. Remember to always consult with a qualified electrician if you have any questions or concerns about electrical safety. Understanding the requirements outlined in the NEC is essential for ensuring electrical safety. Firstly, overcurrent protection is a cornerstone of electrical safety, protecting circuits from excessive current that can lead to overheating and fire. Circuit breakers and fuses are the primary devices used for overcurrent protection. Secondly, wiring methods dictate how conductors are installed and protected. The NEC specifies approved wiring methods for various applications, including conduit, cable trays, and direct burial. Thirdly, equipment grounding ensures that metal enclosures and equipment frames are at the same electrical potential as the earth, minimizing the risk of electrical shock. Fourthly, ground fault protection detects and interrupts ground faults, preventing electrical shock and equipment damage. Fifthly, arc flash protection is aimed at reducing the severity of arc flash incidents, which can cause serious burns and injuries. Sixthly, lockout/tagout procedures are used to de-energize equipment before maintenance or repair, preventing accidental energization. Seventhly, personal protective equipment, or PPE, is essential for electrical workers to protect themselves from electrical hazards, such as arc flash and electrical shock. Eighthly, electrical safety training is crucial for all electrical workers to ensure they understand the hazards involved and how to work safely. Ninthly, regular inspections and maintenance are necessary to identify and correct potential electrical hazards. Tenthly, following manufacturer's instructions for installation and operation of electrical equipment is essential for safe and reliable performance. Remember to always prioritize safety when working with electricity.